and statistic that you need to study higher level courses, especially mathematics courses and other your software related courses. And you will be able to utilize the basic mathematical and statistical concept in your problem solving. Okay. So how you are going to study? Resources for what we are going to provide you. Okay. So the main thing is our course material. We will give you, I would say it's kind of lecture not, but you have all the exercises and activities and solve problems on that course material, on that lecture note. Okay. So in this course, the course material has 5 units. That means kind of chapters, 5 chapters basically you have. And each chapter may have 2 sessions or 3, 4 sessions. Okay, kind of sub-chapters. Okay. So that is the main resource that you need to follow in this course. And additional to that, you will have supportive videos, self-assessment activities, practice quizzes, presentation slides of your day schools, and tutor mark assignments also. And let me give some basic information about not only for this course, but generally for the courses in Open University. So the method is mainly self-learning and independent learning. That means we provide you the course material. So you read it and we give some recommended books also. You also try to refer those things and presentation slides, and we provide you some videos also, recommended videos. You can watch those things and engage self-activities in your course material and the ones that we provide. After that, we have day schools. Day school kind of, I would say, kind of lectures in your language, but it is not actually lectures. You will bring your questions to the, that is the place where you will meet your lecturer. Okay, so you will, for this course, you have 6 day schools. 1 day school is 2 hours. So you will meet, you will discuss your difficulties and queries and difficulties that you meet during the course, during this day school with your lecturer. And for this course, yes, we provide practice quizzes also. So you can try these things and see whether you have understood everything in the area. Okay. So where are those things? Course material and activities quizzes. It is in your LMS. That is where is your class. Okay. We will have a tour later. So let me move. The main thing is assessment criteria. How do you know whether you pass the course or not? Okay, you follow everything and that's not enough. You need to do some tests. So the assessment criteria contain, this is a continuous criteria. First, you have tutor mark assignment. You will have only 1 tutor mark assignment because this is a short course. So it will be an online quiz on LMS. We will open it for like 2 weeks and you will practice those problems and you will answer in the LMS online. Okay. Then you will have a continuous assessment test we call CAT. That is also you have only 1 CAT examination. So it will be 25 minutes. We are planning to have it online and on site. Okay, you can go to the nearest center to take that examination. And you have 10 online quizzes during your day school. You're not supposed to participate to all, but we recommend you to participate to take all the quizzes. Only 6 out of those quizzes, maximum 6 quizzes we will count as your marks. Okay. Then how about the final examination? So there is one more stage before the final examination. That is based on these 3 activities, you are going to see whether you are able to sit for the final examination or not. The criteria we call OCAM, Overall Continuous Assessment Mark. How we are calculating that mark? For this course, This is how we calculate it. We consider our maximum 6 online quiz marks and TMA marks and CAT mark also. That means continuous assessment test. And 0.3 from CAT examination, 0.3 from TMA, your due, and 0.4 from average of maximum 6 quizzes. So this is mathematics. So the best way to understand it is examples. So let's do one and see one example. So let's say your TMA you got 75, your CAT examination you got 65, and for the online quizzes which you faced during the day school, you got these marks. But we are not considering all the 10 marks, we are taking only maximum 6 out of those 10. So I have highlighted the maximum ones from there. So let me plug into the equation. Okay. 65 for the CAT, 75 TMA, and the maximum average. Then you got at then 78 marks, which is greater than or equal 40. Then you can sit for the final examination. That means if your OCAM mark is greater than or equal 40, you are eligible to sit for the final examination. Okay. Here we go for the final examination, and it will be a 2-hour examination, which will be on-site. Okay. Then how will you calculate your final grade? Your final grade will be, if your OCAM mark, final examination mark, final written examination mark is greater than or equal to 40, then your final mark, final grade will be average of OCAM mark and the final examination mark. But if it is final examination mark is less than Y, then it will be just Y. Then how do you know whether you are pass or not? If this overall mark is greater than or equal to 40, then you have passed the examination. Okay. So, hourly breakdown. This is something will be important for you. This I'm planning to explain here how you need to break your time, how do you schedule your studies according to this time slots. For example, I mentioned that you have 5 units in your course material. Totally, you will have 13 sessions. That means sub-chapters. Okay, so for each chapter, we approximately give you like 2 hours to spend to understand theory or read the material. One session, you spend 2 hours. Approximately, it depends on you. And for the day school, I mentioned day school is one day school is 2 hours. So we have mentioned that also here when calculating. You can discuss theory or problems there. Then as activity hours, we have 5 online activities in LMS. I will show it later. And approximately half an hour you will spend to 1 hour. Maybe some activities may take more than that, but depending. Totally, we have separate 2.5 hours for that. Then workshop, this is the workshop. It will be a 4 hours. So you already started your learning process. And independent learning. So you read your sessions and you do self-studies. You practice with activities, use Google and do your other studies. So we have assigned 3 hours for one session. So totally 39 hours. And we have provided some videos, selected videos in LMS. So one video may not 1 hour, but totally together we give like 1 hour videos for each unit. And the assessment time slots, I already explained. CAT examination is 1.25, that means 75 minutes. And online quizzes, one quiz we will like 6 minutes. So totally you will spend 1 hour for that. And one TMA, you may take like around 5 hours for that. So totally around 100 hours you will spend on this course. Okay. Any question regarding what I explained right now? No questions? Okay, then thank you for a few minutes. Okay, there's one in chat box. Let me see what is it. Please highlight that they cannot register for, oh, okay. Yes, I forgot to say that. If you didn't take your OCAM mark more than 40, that means if you are not eligible for the final examination of this course, you will not able to take the first mathematics course, which is basic mathematics for computing, when you register for the degree. Okay, that is MHC 3459 course. So that's the first mathematics course that you will be take when you start the degree. So if you want to take it, you are supposed to take the eligibility of this one. Also, you are supposed to pass this course to take the course MH 4256. Okay. So it is important that you pass this course. Yes, you may not able to register for those two courses, maths courses, level 3 and level 4 courses, because your eligibility and pass depend for that. So therefore, you need to register for this course during your ad drop. Okay. When is that drop? Yes, you will be informed when you are ready to register for that. This course doesn't count for your credits. For GPA, this doesn't count. Okay. So you don't have any question? If you don't have any question, you can ask your friend's question. Ask from your friend and you can ask. Okay, then shall we have a tour in our course? Huh? Okay, there are two questions already given. How to get LMS access? You already have access. So have you logged into LMS before? The mathematics course? MHC 2250, have you logged it and have a look on there? Okay, let me share the So you first go into the give me a second. There are a few questions in chat box. If we get eligibility, we can register to basic mathematics, right? Yes. So then we don't have to pass this subject. No, you need to pass this subject because you need to take MHC 4256 course also. If you are not passing this, then you will not be able to take that course. Okay.
Dr. Nivanti, Please don't answer, any questions not related to mathematics. Those students can ask the questions in the proper LMS place. There's a question about e-fill, so don't ask. Students, please only ask questions about this mathematics course here. Don't
There
ask
is
other
a
questions
special
here.
announcement that I need to make. This course is compulsory only for students who didn't do A level in mathematics streams. So if you're art student, commerce student, or some other student who took for the bio student, then you need to register for this course. For if you have done A level for mathematics for the A level, then you will be okay. Okay, you don't have to register for this course. So, it's not sharing. It's not sharing. Okay, then let's go and have a look with have a look on our course. So, shall we all log into the course? If you have your mobile phones, you can go to openlearn.lk. So, since I already have logged, I directly go to that page. So if any of repeat student need access for this elementary mathematics course, please send a request for us through your LMS. I'm not sure. Forum. Yes, there is a separate forum in general support, so you can have a request there. So if you're having any difficulties to log in from your phone, you can just look at your friend's phone. Okay. You can share. If you have any electrical devices with internet access, you can log in. If you have any difficulties, we have staff there. You can ask for help from them. So, who already logged? Could you please stand up? Only few. How about others? Have you checked what's their issue? Our staff. Is Madhushan here? Someone asking support program general card not showing to them. Only show software industry card.
This is for the repeat student. Are you a repeat student?
I think so.
So
Repeat students will have to use
another course, our learner support course. You can
There is a
ask
learner
anything
support.
from the
Yeah.
learner support. You have access for the our learn OSL learn support course. Then you can access that course and ask any questions from them. And there is another choice to ask access for the this mathematics course also.
If you have already logged into the LMS, shall we go to this link, MHC2250? So please try yourself because we are going to play some games also on here, so you will miss that. So the courses looks like this. Okay, so shall we have the attention for the screen? Okay, so here we have our main 5 topics of your course. Each is linked to your unit or the chapter. So if you visit these links, you will see all the things in one place, like your course material. So in the unit one is the introduction to logic and sets. It has 2 sessions. You can find your notes here, and you have suggested videos. You can watch those and some activity and practice quizzes and discussion forum. So sometimes I may give bonus point for this for having discussions in discussion forum. So please stay in touch with those discussion forum. Okay, just to motivate you. Okay, so likewise for each unit you have similar thing. You can find all the learning supportive documents and information there. Please have a visit to these. And course communication, you can find our contact information, everything here. Screen is not satisfactory. Okay, so if you want any helps on regarding this LMS course page, you can post here. Okay. So this is the place where we are working today. Okay. So I mentioned that you will find online quizzes during your day school. So shall we practice one quiz today? Okay. Shall we go to this quiz time? If you don't have any devices, that's totally fine. You can do it at your home. We are not counting these marks for anything. You can share with your devices with your friends and do as a group. Please have a try on it because then you will see what looks like quizzes in mathematics. Okay. Because you are going to have 2 online quizzes in every day school. That means like every week. Okay. One more thing, you need to take more than 15 points for this quiz to play the game. So try it. So are you done? Okay, then shall we do it together then? Because if okay, you're doing it. Okay, I guess this is the first question. It shows you are here. So if A is 5, B is 7, what is this value? I can't hear. Loud? I got one answer. How about others? Can I have 3 more answers? Come on, hurry up. Okay, you can try it at your home. Okay, I got 2 answers, 31 in chat box. So I invite all of you to do it at home if you didn't do it. So don't, at the end of the quiz, don't click finish attempt and finish the quiz. Okay, and submit it. Yeah, I think now you got some experience on LMS. So shall we start the workshop from now? So let me introduce our resource person first. So as the first event of this course, we have arranged today's workshop. So the intention of this event is to expose you all the beauty of the subject of mathematics. Okay. So as the resource person, we have invited Professor Anuradha Mahasinghe, and I warmly welcome Professor Mahasinghe to this event. Let me give a brief introduction about him. So Professor Anuradha Mahasinghe graduated from University of Colombo in 2008 with first class honor. Subsequently, he earned his PhD from University of Western Australia in 2016 as a collaboration with the University of Colombo. As for his PhD, he has worked on a mathematical study of quantum Borg-based applications. So there are more than 40 research publications published in genome journals to his credits, including 7 research awards. Okay, have you watched Thala movie? Have you watched the Thala movie? Thala movie, sorry. No? Anyone? So, hands up. So it looks like we will have to do some exercise. You are lazy to hands up. Yes, so why did I ask that? Professor Mahasinga has received the Cygnus Award as the best movie lyricist in 2019 for lyrical composition in Thala movie. So he's not just a mathematician, he's also a musician. So most of us has played Athuru Mithuru, right? Have you played Athuru Mithuru when you are young age? Athuru Mithuru? Hands up, please. If you have played Athuru Mithuru in your young age, please hands up. Okay, now I'm going to do Simon Says if you are not acting. Okay. Yes. So, did you ever thought that there's a hidden mathematics behind that game? So I just wanted to say that mathematics is everywhere. So our resource person, Professor Anuradha Mahasinghe, has came up with a mathematical model with the to the Athuru Mithuru game with the algorithm called brute force algorithm. So further, several fiction stories, short stories, and series of articles related to mathematical thinking aim at popular reading such as mathematics, Sinavig, Ganithaya, Hathilantaya, Gantulane Ganitandara, also has published by Professor Mahasinghe. He has also produced several other writings in several literary genres such as Vemithya Kalaya, Kindru Vatunutana, sorry, Blake Newton Situama, Haranimbita Prasadaya. Those are also some of his literatures. And there are many featured also in national newspapers and tabloids such as in Samudura, Manahara, Bidusara, Rivira, and The Nation. Currently, Professor Mahasinghe serves as a professor in computational mathematics in Department of Mathematics, University of Colombo, who is also the Deputy Director of Center of Mathematics Modeling in University of Colombo. So now allow me to formally invite the Professor Anuradha Mahasinghe to stage so that he can continue the session.
Hello, good morning. Thank you so much, Dr. Langvi, for the introduction, and Dr. Langvi, Dr. Kumari, and Dr. Amenika for inviting me to give this talk. So today I'm happy to talk about the humanistic aspects of mathematics mainly. And the title of my talk is actually, you can see the human factor in mathematics. So I have put this title purposely because people view mathematics, so there's a tendency to view mathematics as a subject that you cannot see the human endeavor. So I'm trying to give some evidence that it is not the case. And I would like to view mathematics as a human endeavor, and mathematics not just as a discipline confined itself. So mathematics not for the sake of mathematics, right? And especially, so you are willing to be software engineers in future, and I'm going to talk about how math is going to be very much helpful to you eventually. Okay, so this is actually the focus of my talk today. So mainly I will be talking about the humanistic aspects of mathematics, probably something that you haven't heard before, maybe. Okay, so let me start from this picture and let me ask a question from the audience. So what is your take of this picture? Just look at it. You can view it on the screen. So what do you think? What comes to your mind when you see this picture? Any responses? Yes, anything? Yes, something comes to your mind, right? So I think you recognize this as Yes, as what, as the moment a great discovery is made, as such a moment, okay, in history of what? History of science, history of physics mainly. Okay, so I think once you see this picture, so there's a person sitting under an apple tree, apple falling on that person's head. So you identify, you relate it to Newton, right? Identifying the person as Isaac Newton. So Isaac Newton and the apple falling on Newton's head. The moment that is supposed to be, I think the moment where gravity was discovered, right? All right, so we all accept that science is a collective effort of mankind. Okay, science has this sort of stories. Nice stories are there about the. Also, I have seen recently. I have seen some researchers are claiming that there was no apple tree in Newton's courtyard, and this story is fabricated. So people are even they wonder about the actual. I mean, people have taken these things as facts, but there are stories, the meaning, and there are stories about Archimedes. There are stories about Einstein. So there are stories about scientists, and science is generally regarded as a discipline that comes from human endeavor. Okay, but the problem is mathematics, right? Unfortunately, people do not admit mathematics as as an effort of as a collective human effort. And what is the nature missing in mathematics that we see? Sorry, I have to share the screen. Right? I think I'm sharing. Am I? Yeah, I just went to Zoom and then I want to share this screen.
Try again.
Yeah, you can see this. So we are making many errors, right? Human nature. So means human made. This talk is human made. So the nature of human is to make errors, right? So you have excuse. Let me make it. Okay, I hope it works now, right? So shall we continue? Okay. Sorry for the delay, but you can see to err is human, right? And to forgive is what? Divine. Samavadima, Devagati. So you have to forgive us for the errors, for the human errors we make. The thing is actually mathematics. In mathematics, we don't tolerate errors. It is supposed to be error-free, right? And so I think people think that since mathematics is regarded to be an error-free subject, people tend to see it as something very abstract, something that comes out of nowhere, okay, not as a human endeavor. But I'm going to show you some evidence from history of mathematics that mathematics is also a collective effort, a consequence of collective human effort. And let's see, look into some evidence actually, and the nature of human is actually making mistakes, errors. Yes. And if you look into science, well, there were many debates, many controversies, different opinions in the history of science. For example, if you look at the question, what is light? We have received 3 different opinions, 3 different answers from 3 different centuries. Earlier, it was Newton, as you may have heard. Newton said actually, light is made of particles. So if you use that theory, you can explain certain things. Like, okay, a ray of light, a ray of particles hitting a mirror and reflecting that. Yes, if you regard light as a bunch of particles, yeah, you can explain certain properties of light. And at that time, this was accepted because that was the best theory that explains some behavior of light. And from the 18th century, a different theory came in because the earlier theory could not explain certain features of light. So in the 18th century, Huygens gave a different answer. No, he said, no, light is not a bunch of particles. This is a wave, right? Don't regard this as matter. It's a totally different thing. It's a wave. So because Huygens could explain certain things that Newton couldn't explain, that theory was accepted. So you dump this and you accept the new thing. That's how science progressed. And in 19th century, in the early developments within the early developments of the quantum theory, Einstein brought a new idea, the corpuscular, early it was a corpuscular theory, and then actually the wave theory, then the photons, right? So Einstein brought a totally new paradigm into it. Light is made of small energy packets called photons. So 3 different opinions from 3 different centuries, from 3 different persons. This is the nature of science. Science always changes, and scientists make mistakes. And scientists make wrong claims as well. And then they are corrected. And that is how science progresses normally. So this is about physical sciences, right? Physics particularly, what is light is a question that belongs to physics. And that's how physics progresses. And about the life sciences or the biological sciences, well, there are so many debates. There are so many controversies. If you take the very fundamental question, what is the origin of life on Earth? Well, first Aristotle said it is a spontaneous generation that flies and small creatures, so they actually originated from the inorganic materials, right? Organic things originate from inorganic materials, and that was actually in a way a basis for the some Darwinian theories as well, right? And then it was the natural selection and a totally different idea given by Fred Hoyle and Chandra Wickramasinghe, a scientist of Sri Lankan origin, that is called panspermia. The life came to Earth maybe on a comet, or maybe on a comet, right? So it came from the space. The life is universal, so that it is called panspermia. So likewise, there are different theories about the origin of life, and the debate continues. And there's no unanimous argument about the origin of life in biological sciences. So this is the nature of science. But in mathematics, right? In mathematics, do we have such debates? Is there any debate on the sum of the angles of a triangle? Is there any debate on any mathematical theorem, for example, Pythagorean theorem? So if you apply Pythagorean theorem, and if I apply Pythagorean theorem, and a person from Europe applies the Pythagorean theorem, no difference. So it is supposed to be universal, but sometimes the universality is, the universality is sometimes actually it is regarded as something non-human, something too abstract, something not related to life, right? Because we used to see errors in mistakes, mostly in humans. When you are dealing with humans, we are used to see errors. In science, we see errors. In biological sciences, we see different opinions, different aspects. So mathematics supposed to be this sort of monism is, monism in the sense that you don't see different opinions very often. But I'm going to see some great debates, some different opinions and controversies in the field of mathematics from the history of mathematics. Okay, just to show you that mathematics is also one of the subjects the mankind has invented. All right, so as for this, just a picture. So what do you see? An old woman or a young woman? Those who see the old woman. So I'm trying to show you that it's about the interpretation. So is this an old woman or a young woman? Yeah, we can debate for hours, right? Those who see the old woman, can you see the old woman? And anybody who sees the old woman? And anybody who sees the young woman? Yeah, because you are young, right? I'm getting close to 40, so I'm getting to see the old woman, right? Okay, so different interpretations, the same picture, one picture, and I think most of you are young, so you see the young woman, natural. Okay, so sometimes we see what we want to see, right? Okay, so is mathematics free of opinions? Is it free of interpretations? Or do we have different opinions? So what is that humanistic aspect of mathematics? Now, this is actually what we are trying to say, right? There are interpretations and there are different ways of practicing mathematics. There were some great debates in the history of mathematics. And just one other question. Is mathematics invented or discovered? So do you see the difference between these two terms? So this is also something we can consider. Is it invented or discovered? Now, Edison invented the light, the bulb, right? Electric bulb. Edison invented the electric bulb. So he made something that was not there. Okay, that is an invention. And Columbus discovered America. He didn't invent America, right? He discovered America. So is mathematics invented or discovered? What do you think about the Pythagorean theorem? If you take a right angle triangle, 5, 3, 5, 3, 4, 5, right? That rule, is it invented or discovered? So did Pythagoras invent it or discover it? What do you think? Anybody who thinks it was invented, is mathematics invented? Anybody who thinks mathematics is invented? You see the difference between invention and discovery? So we say Newton discovered gravity, right? An apple fell on his head and he suddenly discovered gravity. Okay, that is a discovery. The gravity was already there. And there's a joke that the teacher taught gravity to students. And the teacher said that it was Newton who discovered gravity. And because of gravity, we can stand, we can stand on Earth like this. Then the students asked, actually, so before Newton, didn't people stand on Earth? Right? So this is the nature of discovery, right? Newton discovered, it was already there. The gravity was there and Newton discovered it. And the electric bulb wasn't there already and Edison invented it. So how about mathematics? Is it invented or discovered? Those who think it is invented. I just want to get a call, right? Those who think it is invented. Math is invented. Come on. Have an opinion. Come on, it's okay to have an opinion. To err is human, right? Don't worry if it is wrong. Making mistakes is human nature. That proves that you are human, right? If you make a mistake. Okay, so those who think math is invented and those who think math is discovered. Okay, thank you so much. Well, this is a great debate in the world, in the philosophy of mathematics. There are two different opinions on this, and there are two schools. There's one school called the school of Platonism, right? Who believe that mathematics is discovered. Now, you belong to that school. And there's another school called constructionism. People who think that mathematics is being invented. Mathematics is a human construction. The theories are not there. We are inventing the theories. There are some laws that govern the universe, but we state those things with assumptions and with our own formulation. So there is another view of mathematics. So most of you being Platonists, it's fine. So why is it called Platonism? Because, have you heard about Plato? Almost everyone has heard about Plato. So what was Plato's philosophy? Plato thought there is something perfect in this universe. For example, there is a perfect rose somewhere in the universe. And what I see in my garden is just an imperfect version of that perfect rose. Okay, that was called Platonism, the philosophy of Plato. And there's some ideal, ideal person, right? And what you have in your home is actually an imperfect version of that. Okay, that was Platonism, applied Platonism. Okay, and that some romances are called Platonic. Why? Yeah, you don't, that it is just something hypothetical, something that exists in your mind, right? Not in practice. That is the nature of Platonism. So in mathematics, glad to see many Platonists here, right? Because you see that straight lines, triangles. So how can I draw a straight line? I think I can imagine fairly why you guys are Platonists. Isn't it due to this reason, right? Now I cannot draw a straight line perfectly because a straight line should not have what? If I draw a straight line, I make mistakes because of my human nature. I cannot draw a perfect straight line. Why? The straight line I draw has a width, right? It has a width. Theoretically, a straight line should not have a width, right? If it's a straight line, it should not have a width. But if you measure it, maybe in micrometers or millimeters, micrometers, so there will be very small width in it. So it's not perfect, imperfect. But Plato assumed, okay, there is some perfect straight line somewhere in the universe. And what you have drawn on your papyrus or whatever, right? It's an imperfect version of that perfect straight line. You cannot draw, you can't draw a dot, right? If you want to draw a point, a dot, no, you can't do that because that has some width. Okay, this is not allowed. You cannot draw a perfect triangle. So this perfectionism, if you want to be perfect, then you have to be Platonist, and you are Platonist. But I'm giving you some evidence to show that mathematics is a human construction. So I'm just trying to drag you to the other side of mathematics. Excuse me, but I have to do that, right? That's my effort. Okay. So yes, Platonism is there. So I'm not criticizing Platonism. That aspect is there, but there's this other aspect of mathematics. It is a human creation as well. Okay, yes. If you think of Euclidean geometry, right? You are dealing with different geometric objects. Well, they are supposed to be perfect geometric objects, but what you draw on papers, not perfect. And what you do on papers, not perfect math. Okay. So I'm just trying to show you that there's this human aspect of mathematics as well. And some people, so I told you earlier that there are two schools. One is Platonist school, who regard mathematics as discovered, right? They think mathematical theories are discovered. And the other school is there, the constructionist school, who believe that mathematics is being invented just as other branches of science. All right. So I'm actually drawing your attention to one great debate that was there in ancient Greece. Okay, so this is a very important point in the history of mathematics. This debate continued for thousands of years. There were two schools. I think everybody has heard about Socrates, right? Yes, at least about the Socrates who committed suicide, and there's even a very nice single drama about Socrates, right? Everybody has heard about Socrates, I suppose. So Socrates school was very strong. That's a very strong school in Athens in Greece. Socrates, Plato, Aristotle. So they actually they were the later followers of the school who contributed to it a lot. Socrates is the pioneer of this school, and there was another school. They were intellectual rivals. They were the enemies of the Socratic school. That was the Parmenidean school, right? There was another school. So whenever they meet on street, what they do? Fight or they debate, right? Okay. Enemies means they don't fight, but they debate. So they had many debates. So Socrates believed that you can break down the entire universe into very small parts. Okay, that was the main philosophy. An underlying idea behind many Socratic ideas was that you can break down the things into small parts. You can discretize. We call it a discretization. On the other hand, their rivals, the Parmenideans, so they held the view that the universe is something continuous. Okay, universe is something continuous that you cannot break down it into parts. And then actually there was a student of Parmenides called Zeno. So he brought a very interesting argument, and he showed mathematically that you cannot shoot an arrow to a target. I will give you this idea. Right? It's something we can easily. We'll try to follow the idea of Zeno. So he has given this idea to counter the Socratic school, as an intellectual reply to the Socratic school. And using this mathematical argument, he showed that it is impossible to shoot an arrow to a target. Okay, here's the argument. Showed that, well, if you want to shoot an arrow to a target, then definitely the arrow should pass the midpoint between the archer and the target, right? The midpoint is there, right? So it has to reach the midpoint at some point. It has to reach the midpoint. And then you measure, then there will be a distance from the midpoint to the target. And how about the half of that distance? The midpoint of this distance. The arrow has to go through this distance as well, right? Okay, and still actually it hasn't reached the target. Still there is some gap, and you have to go to the midpoint of that as well. So always bisecting these things. You keep bisecting, there's always a gap to the target, right? You keep bisecting, because if you start from, before shooting the arrow, the arrow should reach the midpoint, right? And from the midpoint of the target, there's some gap. It should reach the midpoint of that part. And you keep arguing like that. And then Zeno said, the arrow will never hit the target. Okay? So mathematically or philosophically, people were helpless. Although anybody can say that, it is possible to shoot an arrow to a target. Violating, countering this argument. But mathematically or philosophically, how can you give an answer to Zeno? So this was a great debate. And do you see that in this argument, Zeno makes use of something very interesting, that is the infinite summation. This is what we call infinity, right? If you do it for finite times, yes, there will be a gap. But you keep doing it infinitely many times, right? You keep doing it infinitely many times. So if you add these things infinitely many times, does it sum up to this distance? So this was a great debate, and still people are arguing, and people actually, there were later solutions provided to this. But for thousands of years, people struggled with this simple argument. Okay, so this is the nature of mathematics. So some human being comes and gives an argument, this sort of absurd argument, and people are struggling with it for thousands of years. And one great debate between Socratic school and the Parmenidean school, all right? So that debate was there, and I told you that Socrates believed that it is possible to break large things into small parts. And Parmenides thought, Zeno's teacher, right? Zeno is the person who gave this argument, and Zeno gave this to support his teacher. So Zeno's teacher believed that it is impossible to break down large things into small parts. So the problem is actually, once you break this into small parts, this leads to something absurd. Okay, if you divide the space into small parts, that leads to something absurd. So this was what Zeno wanted to show, maybe, right? Okay, he gave it to support his teacher. So this is one great debate in mathematics, and later on when mathematics developed, with calculus particularly, with infinitesimal calculus, this idea became central. And actually, there were many attempts in calculus, and modern calculus was developed to answer this question. So this became very important even after 2000 years. This thing, a very simple argument, but of course, very nice argument, right? With controversial argument. So this is one great debate in the history of mathematics. And then now, actually, I'm just showing you another great debate over the infinite summation. So you have to sum up those things infinitely many times. What do you think about this summation? So you see something on the screen, something very simple. 1 minus 1 plus 1 minus 1 plus 1 minus 1. Alternatively, you have 1 and minus 1 alternatively, and there are infinitely many terms, right? You know infinity, right? Yes, there are many terms, infinitely many terms, unending chain. So what should be the summation of this? So this was also a great debate in mathematics. We don't see these things in our textbooks, right? So these are hidden from the textbooks. But there was a great debate, and great mathematicians were divided in opinion. Great mathematicians in 17th, 18th centuries, So they were divided in opinion. And actually, you see this Guido Grandi. So he was a priest as well. He was a mathematician, an Italian mathematician, and also he was a priest. So he gave this solution. And do you see that actually you can sum it up into alternative ways? First, you single out this one, right? You can single out the first one from this series. You single out the first one, and okay, just single out the first one, and from the second and third term, right? Negative 1, 1, negative 1, 1, negative 1, 1. You can cancel off all the terms. Agreed? You single out the first one, right? This one is there. I think it's very simple. You keep the first one and then go to the second and third terms will cancel off each other. Negative 1 to 1. Okay, and then actually fourth and fifth terms, they also cancel off. So the summation, you can argue the summation is equal to 1. Can't argue like that? Because the singled out one will remain, the others will be 0. And then the second summation, second way of summing it up, right? You can sum it up in the second way as well. In that arrangement, that is just a rearrangement. You take the first two terms, 1 minus 1, 0, 1 minus 1, 0, 1 minus 1, 0. So the second way, you obtain the answer as 0, right? So in the first way, it leads to 1, and the second argument leads to 0. So shall we take a poll? Anybody who thinks it is equal to 0? So what should be the summation? Anybody who thinks it is 0? So the first one gives 1, second one gives 0. Anybody for 1? The first one? Anybody who thinks the summation should be 1? Nobody. Summation from the first rearrangement is equal to 1. Anybody who admit 1? Nobody admits. Second one, 0. Anybody for 0? Thank you. It's okay to make mistakes to us human, right? You are human, right? You can make sure that you are human. So it's okay to make errors. Anybody for 0? I think there were a few for 0, right? Good. It's good. Okay. Okay. Well, don't shy away. And there's nothing to be ashamed because great mathematicians, some great mathematicians believed it is 1. Some great mathematicians believed it is 0. Okay, so well, you are in their position if you think it is 1 or if you think it is 0. They also held the same view, and this was a great debate in the history of mathematics. Come on, once again, do you feel it is equal to 1? Anybody who feels it is equal to 1? Nobody feels it is equal to 1? Yeah, great. Okay, one person who feels it is equal to 1. And there was a great mathematician called Bolzano. So he regarded 1 as a correct solution to this problem. Incorrectly, but Bolzano regarded 1 as a correct solution to this summation. Okay, and there were a few for zeros, right? Couple of hands for zeros. Good. And this person, Guido Grandi, who was a priest, adhering to his religious views, because something comes out of nothing. Okay, according to his religious views, he thought, okay, from the void you can generate something, something non-zero from 0, right? So large things generate out of the void. Adhering to his religious beliefs, Grandi said it has to be 0 because the summation has to be 0. 0 gives rise to something non-zero. To that. And now actually there was the great mathematician called Leibniz. Anybody who has heard about Leibniz? Leibniz was a great mathematician. Normally, you haven't heard about mathematicians. It is not your fault. You have heard about scientists, right? If I say a few names like Louis Pasteur or Isaac Newton, Albert Einstein, yes, you know these names. But have you heard about mathematicians? No. But that doesn't mean there were no mathematicians. There were great mathematicians in history. Leibniz was one great mathematician. He had, it is believed that Leibniz invented the branch called calculus in mathematics. And sometimes the credit goes to Newton as well, but Leibniz's works are very, they're actually elegant in nature. So Leibniz thought like this. Oh, I recall one incident actually. Well, there's a confession I have to make. I think I have copied that a term test somewhere, some sort of examination when I was at school. I have copied. There were two bright guys in front of me, and one person answered one multiple choice. One person answered one. This guy answered three. I think I chose two. The average. I remember something exactly. Okay. So Leibniz actually adopted the same view. So he said, okay, one is one solution, zero is another solution. Take the average, half, right? So 50% say it is one, 50% say it is zero. You take the average, it is half. So Leibniz says it half. Yeah, now we can laugh and we can make fun of it, but Leibniz, a great mathematician like Leibniz thought it is equal to half, basing on the idea of average. So isn't it human to make mistakes, to do experiments, and to have opinions, and to make mistakes and to rectify them later? This is the nature of human, okay? So Leibniz is one of the greatest mathematicians mankind ever had, but basing on the idea of averaging, he gave the solution after this. Kind of unlikely. Yeah, a little unlikely, but this is the nature. These are the things that you don't see in textbooks. If you look at the history of mathematics, there were many errors, there were many mistakes. So mathematics is, after all, it is actually something invented by the mankind. I mean, the mathematics you see, maybe we are investigating the laws of the world, the laws that governs the universe, true. But you cannot deny the fact that mathematics, as it is, the form of mathematics we practice, now it is actually an invention of the mankind. There were many errors, opinions, and then rectifications, correcting the errors. So those things are there in the history. And since we talk about Leibniz, Leibniz was, a kind of equivalent to Newton actually in science. Newton is a leading figure in mathematics. Leibniz is also a leading figure, and I'm showing you one of the writings of Leibniz. So he wrote in both French and German. He was a German. Leibniz himself was a German, but he wrote in both French and German. So this is one of Leibniz's texts in French, I suppose. I think so. Yes. Okay. So here Leibniz argues. So he was actually against the number-based state. So we are using number-based state, right? I'm just showing that mathematics has opinions. In physics, there are opinions. In biology, there are opinions. Now, the term in biology, I mean in physics, right? Have you heard about Big Bang theory? Big Bang theory, right? I think everybody knows what Big Bang theory is. What is Big Bang theory? Can someone answer? What is your take of Big Bang theory? I'm not referring to the TV series, right? No, I mean, so they took the same name to the TV series, right? But Big Bang theory is supposed to be, why is it called Big Bang theory? Isn't this colloquial? Isn't this slang? Big Bang. It's not the great explosion, right? It is not called, scientists don't call it great explosion. I think the singular term for the Big Bang theory is Mahavipuram. It is called Mahavipuram, right? So there was the void, there was nothing there. And at some point, well, and you see the light and then you see the universe, okay? And suddenly the universe has been formed spontaneously, something like that. Okay, there was a void and suddenly you have a universe. Well, why is it called Big Bang? Anybody knows this history of this term? My point is, in singular, although it is called Mahavipurama, if you translate Mahavipurama to English, I think the most appropriate way to translate Mahavipurama to English is great explosion, isn't it? Mahavipurama, come on. But it is Big Bang. Why is it Big Bang? Very slang, right? Very colloquial, it's slang. Because this was a term used by Fred Hoyle, one of the great scientists, to make fun of this idea. Oh, it is a Big Bang, right? He was ridiculing, he was making fun of the idea. Right? Was making fun of the idea. Oh, you have nothing at the beginning and suddenly you have a great universe. Oh, you're Big Bang. So he was ridiculing the idea and the press adopted that term. That is why it is known as a Big Bang today. So different opinions. So Fred Hoyle, actually, he never ever believed in the Big Bang, that what great explosion or whatever, right? So he ridiculed the idea, calling it Big Bang. And later on, like the same thing happened to God particles, I suppose, right? It is the word invented by the press. So the word Big Bang became standard later. It became the standard term for that. And that is why it is called Big Bang. I don't think the translation Mahavipurama reflects that that sarcastic aspect of it. Anyway, so this is about opinion on practicing mathematics. Now the mathematical theories are there. The laws of the universe are also there. But how to practice them? You have to write the numbers, you have to write the equations, you have to write numbers on papers. So you have to bring it down to papers, pens and pencils, papers, those things. So as for this translation, Leibniz strongly argued that number base 10 is not appropriate. Now we are using base 10. We are writing numbers to base 10, right? Why? Why is it base 10? Anybody has any idea why are we using base 10? Why has this exactly? It is widely believed that people use base 10 because we have 10 fingers, exactly. So you count, okay, you want to count 1, 2, 3, 9, 10, and then you start from this level. So this is supposed to be the reason for adopting base 10. But there were different civilizations, some ancient civilizations who adopted different number bases. And Leibniz argued the best number base is 2, binary. That was Leibniz's argument. Okay, and there's something very interesting how Leibniz came into this argument. There were several factors, but I just wanted to show you something from the history of mathematics, that Leibniz was a fan of Chinese history and Chinese mythology as well. Actually, he had many Chinese friends there. He was corresponding with China those days, right? Even now we do it a lot, right? Those days Leibniz wanted to contact Chinese, not the other way around. So he actually wanted to convince some Chinese that Leibniz's philosophical ideas, right? He wanted to convey some of the philosophical and religious ideas with his Chinese counterparts. Okay, so he had lots of correspondence with China. So he received this ancient text, a kind of secret message, something that is believed to be written by the first king of China, right? According to Chinese mythology. Well, according to mythology, so there were ancient kings, like in Sri Lanka we have Ravana, right? Okay, likewise in any culture, so they have their ancient king who ruled the world, and every nation is superior, right? In their own literature, every nation is superior. So like we have Ravana, in India they have Rama, and so in China actually they have a person called Fuxi, right? Who was the great king of China and the entire world according to Chinese. So Ravana ruled the world. No, same philosophy applies there. It's human nature to make mistakes. Okay, so these are the numbers supposed to be written by that person, the person who ruled the world, called Fuxi, right? So Fuxi has written these things. So Leibniz received this probably from his Chinese friends. Okay, then Leibniz actually recorded this. So what do you see there? This image. You see actually, lines, right? Lines, and there are some broken lines, some lines continue, some lines are broken. Okay, so he did something very interesting. He identified, okay, it makes of actually, if you look at this very carefully, you realize that you can break it into 8 parts. Okay, so Leibniz broke it into 8 parts, and there you see, in the first one you see 3 dashed lines. Okay, so I'm just showing you how Leibniz came to conclusion that binary numbers were adopted in ancient history of mankind. So he divided it into 8 parts like that. The division is there, right? In the original one, the division is there. Why can't I go on to the previous slide? Yes, you see, here it is. You see the division is there, but we don't see it because we tend to see 3 lines. But Leibniz was, he was clever, better than us, definitely. So he saw, well, there are 8 elements. And in the first element, what do you have? 3 dashed lines. Second element, 2 dashed lines and 1 solid line. And third element, 2 dashed lines, 1 solid line, 2 dashed lines. And then actually, likewise, you can see, right? 3 elements, either a dashed line or a solid line, right? Then Leibniz showed that if you replace the dashed lines by zeros and solid lines by ones, then it is the binary numbers from 1 to 7. You see? Just replace the dashed lines by zeros and solid lines by ones in order from 0 to 7. The first one use, binary numbers, right? So if you want to write numbers in base 2, in numbers in base 10, I think everybody is familiar with number base 10. In number base 2, it is called binary, and so it is based on the powers of 2. 2 to the power 0, to the power 1, 2 to the power 2, right? So 2 to the power 0, that component is 0. 2 to the power 1, the component is 0. That is number 0, right? And you see the second element, the second object here, the second object, 2 dashed lines and 1 solid line. So replace the dashed lines by 0, solid line by 1, you get 0, 0, 1. Okay, and that is in decimal. What is it? It is 1. And second one, 0, 1, 0. It is that number represented as 0, 1, 0. Okay, 0, 1, 0 in binary is we call it 2. And similarly, do you see that you get all the numbers from 0, 1, 2, 3 up to 7. Okay, so Leibniz argued these ancient Chinese people have used dashed lines represent 0 and solid lines represent 1. So they were the numbers they used. So it is the binary numbers that the ancient people used. And he argues it is easier to use binary numbers. Right? Can someone call any advantage of using binary numbers? Is there any advantage you can recall on using? Have you done binary numbers for mathematics? Grade 8 or 9, I suppose, for IT at least? IT course, maybe, right? Okay, so is there any advantage of switching to binary? I mean, many disadvantages, but any advantage of switching to binary? Yes, the thing is actually, in binary, you don't have to memorize a lot. Multiplication table becomes very simple. Chakra because all the rules you want to know. 0 by 1 is equal to 0, 1 by 1 is equal to 1, that's all. Right? You don't have multiplication tables. But the thing is, if you want to do the multiplication, there will be so many rows and columns, right? So you shouldn't get exhausted, but you don't have to memorize a lot. It's simple memory, right? It's a simple memory, but on the other hand, the compromise is, well, many calculations will be there. You should not get exhausted. You keep doing it. And I will just show you a binary multiplication table here. Here you want to multiply, what is this number? Something like that, you have to put 2 to the power 0, 1, 2. Likewise, you can find the number. So just multiplying two numbers. So this is a binary multiplication table, but you don't have to memorize. You don't have to memorize those lengthy multiplication tables. So that advantage is there. So Leibniz argues you don't have to memorize a lot, something like that. So he argues that he calculates in binary. He did. The great mathematician Leibniz adopted binary numbers. He didn't use decimal numbers for calculation according to his writing. According to what I have shown you, there he argues that I'm using binary numbers. And why can't the world use binary numbers instead of these decimal numbers? A much elegant representation of the number system. So that was his argument. So I think now, well, you may be bored now. I think I talked for a while. Well, there's a small activity for you, right? I hope you remember binary numbers, a very small activity for you. If you have time for this activity, you got your smartphones, right? Yeah, normally your generation is not seen without smartphones. So I assume you got your smartphones. Okay, then you can log into the, I think your LMS or whatever, the system, and the activity will be there. And actually you don't have to use smartphones. They are not necessary. If you want, you can log in and see the same thing using your phone. But you see that on the screen, this is a message to you, a secret message. Now we have talked about binary numbers, and you have seen how Leibniz deciphered that secret message. Okay, so here's also a small secret message, a kind of fun activity for you. Try to decode this, and that's it. And we'll continue after that.
You can find this in LMS. So under workshop, you can find it here. So if you want to have the full screen, you can click here. So what you need to do is try to identify what is the letter which represent black box, white box, and three black box. And find that letter from here and drag it and drop it here. Like this. So I hope our centers also working on the activity.
Dear repeat student, now you also can access the page. Please log into the www.openlearn.lk LMS and please select the Bachelor of Faculty of Engineering Technology. Then select the BSc 2023-2024. Then select this maths course and you can enroll using. Please tell them. Postcode.
MHC 2250.
Then please use your postcode as the enrollment key. It is the MHZ 2250. Then you can enroll yourself. Thank you.
So did you figure it out? What is the letter which need to be here in the first place? You can do this as a group activity. Two of you can think of the first letter and the two of others can think about the second letter. Anyone? Would you like to share your answer for the first box? Sorry, I think I forgot to share the screen with others. Yes, so here, so you can drag letters from here and drop it in these places. So I will give I already have given the hint, like first 5 boxes is a letter and second 5 box give another letter. And what is that letter? Did you figure it out? Who figured it out? What is the first one? E. Someone says E. How about others? Any other answer? I'm not asking from our staff. How about centers? Can anyone could figure it out from center? Yes, congratulations. Senut has sent the answer. Unfortunately, the screen was shared. I think you all saw the answer. So we will have to, so it is W. W is which number? Can you count A, B, C, D, E, F, G, H? It is which one? So which number is it? Sorry, what's the number for W? If you say A is the first letter, B is the second letter, C is the third letter, and likewise W is? Okay, I will leave you to you think more than. So, shall we continue or have the break? Okay, we will continue.
Well, kids, the university, you have to learn everything, right, including the welcome. No one is going to give you things for free. Even the welcome has to be earned some effort. Right? And the degree is also, it has to be earned with an effort. No one is given to give you anything for free. And that's why you see demonstrations, right? That's also you have to earn things. The nature of university, right? No one is going to give you things for free. Nothing is free. So even the welcome not has to be earned. So welcome if you have earned it. If not, yes, you are welcome to this program. Okay, shall we continue? You see how to record it. So this represents the number in the binary form, 2 to the power 0, power 1. So 1, 2, 4, 8, 16. You have to sum it up and find the corresponding number, and that represents the relevant number, the relevant letter in the alphabet. With that index, that becomes W, and the second row becomes E. Likewise, you can decipher it, right? Welcome has to be earned, and the degree also has to be earned. No one is going to give it to you. And other facilities also, they have to be earned from the authorities. I'm not telling you how. Excuse me. Okay. I'm just showing you that there are different ways of practicing mathematics. And since Leibniz said it is the binary number base that you have to adopt, right? And I told you that there are civilizations that adopted different ways of mathematics. And here's actually something from Polynesian tattoos. Do you know where Polynesia is? Well, it consists of, mainly Polynesian islands are there below the New Zealand, close to the southern pole. There are some islands called Polynesian Islands, French Polynesia. Most of them are French colonies, right? And the Maori people live there. Have you seen Maori people? And there was a famous cartoon movie called Moana, I think. And anybody who has watched Moana? Girls, maybe particularly. Okay, you will love it. Okay, so yes, Moana, right? So in Moana, have you seen those Polynesian tattoos? The thing is actually those Polynesians are fond of tattoos, and mainly their art, all their artworks are mostly black and white. And they have this common feature. There are many repetitions. Many repetitions. You see, the same pattern is repeated many times. It's like a computer-generated art. So why is it easy to generate that sort of art using a computer? Now it looks like computer art. It looks like ancient Polynesians had computers. No, they didn't have computers, but they had something similar with computers. Okay, so why is it easy to generate this sort of thing using computers? Yeah, once you have it, then you can write an algorithm. Okay, you can repeat it. Okay, repeat it and repeat, and for one, are you going from 1 to 100? Repeat it 100 times. Repeat it. So repetition is a task that can be easily done with what? Computers. Okay, and why can't we do repetition? Yeah, we get exhausted. Humans get exhausted when they do repetitions, but computers don't. They don't get exhausted. So we use computers to do the same task over and over again, right? So in these Polynesian tattoos, you see this nature. And do you know this interesting fact that the ancient Polynesians used binary base for counting? They had a binary civilization. They used binary numbers. So to multiply, they did not, when they multiplied, they don't get exhausted. They do the same thing again and again, they don't get exhausted. So this is what they share common with computers. They didn't have computers. The ancient Polynesians did not have computers, but this overlapping region was there. There is a binary numbers, the adoption of the binary numbers. If you adopt binary numbers, right, you can't complain about one thing. What is it? Repetition, right? Look at the table. If you want to multiply in binary, yeah, you keep doing 1 0 0 1 1 1 1 0 0. The same task is repeated many times. And as humans, we get exhausted, but the computer doesn't get exhausted. So binary was used as a better base for computing in a computer. But ancient Polynesians also used binary, and their tattoos reflect this fact. They have something common in the computer art. And the reason is repetition. And repetition cannot be avoided. You can't avoid repetition when you are using the binary base. So don't complain about repetition if you use binary. Well, they used binary many years ago. And this is, now researchers have recently found that Polynesians have used binary. So you see that different ways of practicing mathematics, although the mathematical laws may be similar, different ways of representing mathematics and different ways of practicing mathematics in different civilizations. I just wanted to show you by showing these evidence that great debates about mathematics, right? Different opinions in mathematics and instances where great minds made mistakes in mathematics. So mathematics has this aspect as well. So it is actually, as you can view it as a human endeavor. It is not something that comes out of nowhere. It is nothing that aliens gave to us, right? So it is a collective effort of the mankind. Once you adopt Platonism, okay, you can view the things as imperfect versions of something that exists somewhere. But on the other hand, don't ignore that mathematics has this aspect. It is a human endeavor, and different civilizations practice mathematics in different ways. And their way of thinking, in particular, you think that Polynesian example, their way of thinking is reflected in their mathematics. So the way of thinking affects mathematics. Okay, and nowadays the humanistic aspect of mathematics is coming to get accepted by more people. And there are even journals specifically designed to cater to these aspects, the humanistic aspects of mathematics. One major journal is the Journal of Humanistic Mathematics. The name itself suggests that they are looking into the humanistic aspects of mathematics. And there's another journal, Expositions Mathematics, I think some other language, but the meaning is mathematical expositions, right? And there are some other journals. One is Experimental Mathematics, published by Taylor and Francis, one of the most known publishers in the world. So in this journal, they are focusing on the way you the way you come up with a proof, not the refined product, right? So normally, when you write a mathematical proof, okay, you do a mathematical proof, and then you go through the proof and you see, okay, this step seems to be unnecessary, and this is something redundant, so I will remove it, and I will refine it, and I want the proof to look very nice, right? So they are not saying it has to be nice. So give us the scratch. That's what they say. Right? Give us a scratch. And that will give us some insights about the proof and how you came up with the idea. So this is the human aspect. Because if you refine it too much, well, it looks too good, right? And hard to absorb. Even refined food is difficult to digest, right? Okay, so don't refine it. Give us a scratch. So this is the philosophy of this journal, the Journal of Experimental Mathematics. But what I'm saying is nowadays, even the experts are coming to realize that the mathematics has this aspect. It's a human endeavor. And this famous journal, Mathematical Intelligence, you can see lots of humanistic mathematics things, about biographies of mathematicians, gossips, everything, right? Okay, what you see in science, now it is in mathematics as well. Lives of mathematicians, the absurd things they have done. And actually, if you log into this page run by a mathematician, Professor Alex Casamoy, it's about mathematical fiction. Now, science fiction is there, right? Everybody knows what science fiction is. Now, there's a new genre in literature called mathematical fiction. So mathematical ideas are coming into fiction. And if you log into just go to the website and see, right? Just go to the website and see. And there will be a huge collection, a large database on mathematical fiction run by a mathematician, right? And the thing is, so mathematics has this aspect, and I prefer to view mathematics as a result of human endeavor. Okay, so this aspect is there. But there's feature that makes it distinct from other disciplines, mainly sciences. So it is not the fact that mathematics came out of nowhere, no. It is a human effort, right? A collective effort. But there's one feature that signifies mathematics and that makes mathematical distinguishable from other disciplines. That is the approach in mathematics. The rule of acceptance. How we accept something in mathematics. Okay. Normally in science, I think you have heard about controlled experiments, right? Controlled experiments. You have to observe something and you do the experiment, and there are observers, and finally you come into a conclusion. Okay, so you have heard about the method in science. And in science, it is mostly the inductive deductive approach. But don't panic, right? It is called the inductive deductive approach. I'll explain to you what it is. And definitely don't panic when you hear words, right? Don't do that. So every word can be explained in simple terms. So the idea of inductive deductive logic is like this, right? This is about deductive logic. I will go on to inductive deductive logic. Okay, now think about Newton, right? So apple falling on Newton's head. Newton realizes, okay, apples fall and coconuts also fall. So the things, when you release things at a height, they fall, right? Okay, and they keep falling, they always keep falling. And whatever I raise to a height will fall if I release it, right? Because all the things I have seen in the past, all the objects that I have raised to some height have fallen when I release them. So the next object, so if I lift this pen, the same thing should happen to this pen as well. This is the inductive logic, inductive method. It happened in the past. So sun rises from the east. It always rose from the east. So even tomorrow, sun is going to rise from the east. That is the inductive argument. Okay. You refer to past data. You refer to past observations. And you suppose the same pattern will continue or the same thing will happen tomorrow. That is called inductive method. Okay, right? Simple, right? Something very simple. Apples, coconuts, everything, everything that were in great heights, they fell down. So the same thing will happen to everything, including to us, right? Okay, so that is inductive argument. But on the other hand, deductive argument is, okay, deductive argument says, don't base it on observations, base it on logic, right? So science is a collection of inductive and deductive arguments. For example, Newton's law of gravitation. Newton observed things falling, okay, things fall apart, okay. So this will happen to whatever I raise to a height, and this is inductive argument. Then he formulated the theory of gravitation, the law of gravitation. Then it is a deductive science, okay, and it is a formula. And once you hypothesize, okay, every object should obey this law, and then it becomes logical. And once you do a mathematical calculation using Newton's formula, it becomes a deductive argument. So in science, both inductive arguments and deductive arguments are used. But in mathematics, the distinct feature in mathematics is it is mostly or almost all into deductive arguments. We cannot rely on inductive arguments. So this is actually what makes mathematics distinct. Not that it is not a human, made something man-made. No, mathematics is, well, this mathematics, whatever we practice is man-made. So I mean, it was not given to us by somebody supernatural or somebody coming from another world. No. So it was people who created this sort of mathematics. But the thing is, in mathematics, a distinguished feature is we do not rely on merely inductive arguments. We cannot rely on past data, right? We cannot assume the past patterns will continue in future. So this is the distinguished nature about mathematics. And this is the deductive logic. So that is inductive logic, right? So things fell and this pen will fall, is inductive argument. So this is deductive logic. Socrates is a man, the standard example, right? The typical example. Anybody who has done logic for advanced level? Logic, anybody who has done logic, taken logic as a subject? No, I'm not asking a question, I just wanted to see, right? Nobody has taken logic as a subject? Nobody. All right. So this is actually something standard, a typical stereotype, a typical example given in logic to teach the deductive method. Socrates is a man. All men are mortal. Maybe coming from the types of Socrates. Therefore, Socrates is also mortal, right? Okay. So this is a very deductive argument, a logical argument. Well, all men are mortal, right? So mortals. And Socrates is all men are mortal. Socrates is a man. Socrates belongs to that. All men are mortal. Then Socrates is also mortal. Deductive argument. Right? Logical, purely logical. And did you see anything related? If this is the case, then that happens. Deductive argument. In inductive argument, that was not there. Basing on data and coming to conclusions, assuming the pattern will continue is called inductive argument, right? Inductive logic or inductive reasoning. And in contrast to that, in deductive method, we are basing it on logical conclusions. All right. Yes. So this is the difference. Now, why can't we accept the, come on. Yes. In deductive arguments. Now, you have logic as a subject, I think, as a component in your course. So mathematical logic is very important, right? Mathematical logic is not done by people, not even by the people who have taken combined mathematics as a subject. So don't panic. Even they don't know what it is, right? So don't think that they will outperform you, because this is something new to everybody. Mathematical logic, the very foundation. Unfortunately, we don't have the very foundation even in advanced level, right? You have to come to the university to learn the basics of mathematics, basics of mathematical thinking. That is the deductive logic, deductive arguments. And there's such a thing called the implication. If this happens, then that happens. If it rains, then the river will overflow, right? Things like that. We call them conditional statements. And this is actually what we call a truth table. If this happens, then the other thing happens. Okay. Now, this is the difference in mathematics. In mathematics, we don't have very strong opinions or very strong conclusions. Why? The reason is, if this happens, then the other thing happens. That's all. For example, think of the Pythagorean relation. So what does it say? The Pythagorean relation says, okay, take the numerical example. You have a right angle triangle, right? And if this side length is 3 and this side length is 4, the hypotenuse, length of the hypotenuse is equal to 5, right? If cos there, right? If this is 3 and this is 4, it is 5. If then, it's a conditional statement. So the theorems in mathematics, right? The theorems in mathematics and the results in mathematics, they can be almost all of them, except for a few things. There are some exceptions, I agree, but almost all these things you can restate as conditional statement. If this happens, then the other thing happens. If this is 3 and 4, hypotenuse, length of hypotenuse is equal to 5. Right? If this happens, the conditional, we call them conditional statements. And here's an example. If you get 100, but we have to be very careful when dealing with conditional statements. And here's an example, right? If you get 100% on the final, then you will get an A+. Agreed. Yeah, if you get 100%, obviously you get an A+. But the conditional statement cannot be used the other way around. Okay? So we say P implies Q. And that's what you see in the truth table, and we will do some Boolean logic as well. So I'm not going into details. I'm just showing you that this is the idea behind many mathematical theorems. If this happens, then the other thing happens. But it doesn't imply the converse. It doesn't say the converse is true. Now, if you get an A+, right? There's a story. Now, the father tells the kid, well, the father tells actually, if you don't eat the vegetables, the green on your plate, I won't give you any ice cream. Okay? You know, as fathers, well, I'm not a father and I have no intention to become one. Well, the fathers normally say those things to kids, right? Okay? So if you don't eat the vegetables on your plate, I won't give you any ice cream. Yeah, okay, one day when you're fathers, so you tell that to your kid, don't worry. The kid eats the vegetables, and then the father says, no, I don't have to give ice cream, because what I said is, if you don't eat the vegetables, I won't give ice cream. I didn't tell you what I will do if you eat the vegetables. Right? So this thing, the implication. This doesn't mean actually, okay, if you get 100%, you get an A+. But if you get an A+, does it mean you get 100%? No. It can be 95 or 90. I think A+, if A+ is given from 91, right? Yeah, 92, whatever, right? So we have to be very careful when handling with, when dealing with conditional statements like the kid, right? The kid was not careful and he ate the greens on the plate, and yeah, he didn't receive an ice cream. Logically, the father is justifiable. Okay, if you don't eat the vegetables, I won't give you any ice cream. So I didn't tell you what to do if you hate the vegetables. So be very careful. So likewise, mathematics is about paying attention to tiny details, right? It is not about the calculations that you have encountered, the lengthy calculations, or that bizarre geometric constructions. Honestly, I also hate them. When I was in grade 10, my mathematics was not good actually. So I honestly didn't like the mathematics that was there in the textbook, and there were very difficult geometric constructions, and just one thing, I still hate that Sulubali, even now I don't like to take even financial mathematics courses also because of that. The thing is actually the mathematics. Later on, I came to realize that mathematics is not what it seemed to be. It was about paying attention to tiny details. It's about exploring the logical rules behind things. It's about formulating the world and attempt to formulate what you see in a different language. It's about translating things into equations, right? Mathematics is that. It is not the cut and write things that you see in textbooks. So don't worry if you were not good at mathematics when you were doing your O-levels. Because I wasn't good. When I was a kid, actually, well, not a kid, a teenager, right? When I was a teenager, I wasn't good at mathematics until maybe grade 11. At one point, I realized mathematics is not what you see in textbooks. Okay. So until then, I also hated mathematics. and I was very poor in mathematics, and later on I grew some passion, and well, I ended up becoming a mathematics professor eventually. So the thing is, yeah, you also, so just take my word, right? Just take my word. Mathematics is about paying attention to tiny details, and don't think that the others will outperform you. There's no competition, because people are reluctant to pay attention to tiny details. It's about taking things logically, coming into logical conclusions. It's about that. Just take my word. Okay. And yes, so the converse doesn't need to be true. So we have to be very careful. And the inductive method. Think of the inductive method. I'll show you why we cannot rely on the inductive method as mathematicians. Well, this is inductive. If I ask you what the next number is, 1, 3, 5, 7, and you will answer, right? That's inductive method. You see the pattern and you assume, and the next number is, yeah, you say that the next number is 9, right? But what if I say, well, suddenly the pattern breaks and it's a new pattern starting from that and new number, and it's not 9, it is equal to 2023, right? Something like that. Yeah, you can even write a formula to justify it, right? Okay, so we assume the pattern to continue, and well, we are actually we are tempted to say it is 9, but who knows? Okay, and so this is actually just one. I just wanted to show you some examples of inductivism. The inductivism. So you obtain a domain and you look at the data. Let's not go into all the details in these slides. I just prepared them, and to be honest, I copied from one previous presentation. That's why too much text is there. Just ignore it. Just ignore it. I just wanted to show you why inductive reasoning doesn't work particularly. Here's one good example. Just have a look. Right. You see, in 1769, long ago, right? Few centuries ago, even, Leonhard Euler he was a leading mathematician, right? You see Euler's name very often in mathematics in different branches. Euler's formula, Euler's formula and Euler's relation, Euler's whatever, Euler's graphs, lots of things are there. So Euler thought, and he wrote that there is no whole number solution to this this equation. Right? A to the power 5 plus b to the power 5 plus c to the power 5 plus d to the power 5 is equal to b to the power 5. You know what all numbers are, right? Starting from 1, 2, 3, counting numbers. Right? Euler said, you cannot find 5 counting numbers A, B, C, D, E. Right? Euler said you cannot find 5 counting numbers satisfying this relation. Okay? Very reasonable, because if you take this 1, 2, 3, 4, 5 or 10, 15, whatever. No, but later on, 2 persons discovered, later on in the since 1969, with the aid of computers, I assume, they discovered 27, 84, 110, 133, 140, satisfying this relation. Euler was wrong, proven using the aid of computers later. What happens if you rely on inductive logic? If you rely on inductivism, you try it for this number set. Okay. Okay, it will not satisfy, and you take another number set. You keep repeating the experiment, and the relation is not satisfying, and you conclude, okay, there are no numbers satisfying. You make a mistake, right? So that is why we cannot accept the inductive reasoning as the method of mathematics. If you want to accept something in mathematics, that has to be the deductive reason. You have to use the deductive reasoning. And it is the mathematical logic that consists of the idea of deductive reasoning. So learning mathematical logic is very important. I just give you my word, never ever skip the mathematical logic. It is not difficult to understand. And don't think that anybody will outperform you, because even in our advanced level mathematics curriculum, mathematical logic is not there, right? So you are on equal grounds with the guys who got A passes for combined mathematics, right? So I have seen many people who have obtained A passes for combined mathematics in advanced level, but failing to understand logic. On the other hand, I have seen people who haven't performed very well for mathematics at all, but who can understand logic very well. Okay, so it's about the way of thinking. It's about logical thinking, not about handling numbers, not about dealing with large equations. No, don't think mathematics is about dealing with large equations. No, it is not. At this level, definitely it is not. There are calculators in the class. Right? Computers and calculators are there to do their task. So you have to be very keen, and you have to be very smart, and you have to be, you have to be competent in handling things logically and reasonably. Right? And you don't rely on patterns. You don't rely on presuppositions. You don't rely on assumptions. No, because that may be wrong, right? If you see the pattern 1, 3, 5, you don't conclude it as 9 unless you rely on some deductive argument. Okay, so you see what happens. So these are called conjectures. Until disproven, they are called conjectures because it seems to be true, but it doesn't need to be. It doesn't need to be true, and it is disproven. Just one example. So they are called conjectures. Some conjectures are disproven, and a few conjectures are proven, right? So this is actually the difference between mathematics and other sciences mainly. We have to be very strict here. Don't just take the inductive reasoning. It is the deductive method that we accept in mathematics. That is the difference. Okay. And here's another famous conjecture, Galois conjecture. I think not proven, right? Galois conjecture, something from number theory. I just wanted to show you conjectures and the way of proving and disproving things in mathematics. This is what makes mathematics significant. Okay. It is not the fact that mathematics comes out of nowhere, not that mathematics given to us by some supernatural person. No. In mathematics, if you want to counter a general claim, you just have to give one count example. Now you will see this with formula equations when you are doing the course. But just take this example. Somebody says all birds can fly. If someone says all birds can fly, now you want to counter that. You want to build a counter argument, right? You want to falsify that person. What do you have to do? Someone says all birds can fly. You just have to give one example, right? When there is a statement that generalizes things like all birds can fly, if you give just one count example, we call it a count example. Just take emu, right? There's a bird called emu. You know the bird emu, right? The emu cannot fly, right? I think ostrich cannot fly, right? I suppose ostrich, emu, there are some birds who cannot fly. So if someone says all birds can fly, you just give this one example. Okay, just take ostrich cannot fly, and that statement becomes wrong. Okay, so this is how to falsify things in mathematics. Now go to that example, this one. Now, Euler assumed for all the numbers, for all the integers in the world, for all the whole numbers in the world, you cannot satisfy this relation, right? It's like all birds can fly. And two persons, Landa and Parkin, so they found the ostrich. They found ostrich, right? Okay, there's just one tuple, one phi tuple, satisfying this relation. So this is how to prove and disprove things in mathematics. You understood it, right? Come on, you understood it. So, so this is actually the way of proving things in mathematics. So believe me, there are many people, unfortunately, in my faculty who are coming from the mathematics stream. So I have to confess here. I hope they are not leaving this, so I can say this safely. So there are many people in my faculty who do not understand this simple thing. Right? When I grade answer scripts, when they are supposed to disprove something, if I don't ask if all birds can fly, but I mean something similar to that in mathematical language, and if they are supposed to disprove it, well, they give lots of things, try to generalize it, okay, take one word. No. Just give one example, right? Euler said, for any phi tuple, this forms. You cannot find a phi tuple, right, satisfying this relation. And two persons giving just one example, Euler is falsified, right? Okay, just one example is enough. You give the ostrich, and that is falsified. So you understood it, but there are many people who assume themselves to be, who regard themselves to be experts in advanced level mathematics, right? But who don't understand this simple thing. So it's not about mathematics. The other thing is, mathematics is not about complicating the things. It's about simplifying the things. So it's very plain, right? It's plain as water, very clear. Anybody can do it if you adhere to the logical methods, deductive. Once you accept, once you understand the rules of the game. Where are the rules? Mathematical logic, right? The rules are there in mathematical logic. You will have a module on mathematical logic. So you have to take it very seriously. Don't take it loosely. Okay? In mathematical logic, you will learn the set of rules. If you know the set of rules, you can play the game confidently, right? Just play the game confidently, but don't skip the rules. Just learn mathematical logic very carefully. So I was a person who was very poor in mathematics, but later I could absorb the logic very easily. I was very fond of it when I was learning it at the university. Then I think I did well. And so that was a secret, right? Never ever skip logic. This is where the rules are set, right? Learn the rules, and then you can go to the playground. And don't think that the others know the rules. Then they also don't know the rules, right? Maybe you don't know the rules now, but once you enroll yourselves and once the semester starts, you will know the rules and never ever skip logic classes. And don't just try to compromise. There's no compromise on logic. Either you understand it or you don't understand it. Don't think that understanding logic partly helps you. No, it doesn't help you. Either you understand it or you don't understand it. If you understand logic, then mathematics will be, it's plain as water, right? Crystal clear, plain as water. But of course, don't pollute it, right? Well, so these are the things actually I just wanted to show you before the break. So in summary, this aspect is there, it's a human endeavor, and actually the humanistic aspects, so they are gaining more attention than ever these days. So don't think it is very abstract, not related to life. No, it is coming from humans. There were many debates, there were many historical facts also behind mathematics. And what makes mathematics unique is the deductive reasoning, right? And the deductive reasoning is taught in the logic module, and it is very important to follow, right? And the foundations of mathematics, foundations like they are in logic, right? So these are the things that I want to summarize from my talk from the morning, and there will be another session after the break, I suppose, right? Okay. Yeah.
Thank you, Professor Mahasinghe. So we are going to give you a half an hour break. So after the break, please come back. You will see more interesting things. We will continue till 1 o'clock. And your refreshments are ready in downstairs. You can go and enjoy. Okay, then see you again soon. Okay, sorry, I was unmuted there. Please be group, 6 students for one group. You can have more. For example, I think if the center has only 9 students, you can be in one group. So again, please log into your LMS course because everything is there. So you need to stay in touch with that. So if you don't have a device, please join with one of group. Yeah, you can join with anyone, any group with that you like. So what you are supposed to do is, we have uploaded 3 videos here. GA video 1, GA video 2, and GME group activity. Okay, I just showed it. It is under workshop. So you can, 2 of you watch one video, and it is interactive videos, some YouTube videos. So try to understand what they say and do answer to the question that that it's asked. For example, sorry. So in this video, first video, at this point you are asking a question. So try to answer to that question being pairs, like 2 of you can watch one video. So likewise, each group member can watch 3 videos, and we would like if you can share your ideas and share your knowledge with your remaining group members. Okay, so 2 of you watch first video and another 2 of you watch another second video, and the remaining 2 watch the third video, and you share your knowledge with others. Okay. So you should be able to explain what was in the video to your group members after you watch the video. Especially in the third video, there's a question. So I would like to know your answer for that. As one group, you can answer to that question. It is in HE video 3. So is it clear what you're supposed to do? So you group 6 students for one group, and 2 students will watch the first video, another 2 will watch the second video, the remaining 2 will watch the third video. Then at the end you share your knowledge with your friends. Friends mean group members. So for those who just came to the hall, I will explain what others are doing. So please log into your LMS page. There are 3 videos there. So 2 of you can watch video 1, and other 2 can watch video 2, and try to explain what is in video 1 to the other 2 of your friends. Okay? So it looks like you guys are watching all the videos, not explaining to others. So what the thing is, tell your friends to explain what was in the video and go home and listen to that video and see whether your friend lied to you or not. Whether your friend explained to you is correct or not. So watch that video later and see how you can understand things. Okay? So do you prefer to watch a video or read a book, or prefer one of your friends' knowledge? Yeah. Also, another thing, as a teacher, what I got my experience is I learn many things when I come to teach. Okay? So if you explain something to your friends, then it clears what is saying in theory or what is behind the picture more clearly. Because without understanding, I can't explain something to others. So it is, from my experience, I will say, try to discuss with your friends all the things, all the materials that you learn. Then that will increase your knowledge and it will motivate you to learn. Okay? So that is what I wanted to do from this activity. always stay in touch with your friends and discuss and share your ideas. So let me go to the last video. There is one question here. Is this true or false? Can we write 100 as a sum of 5 odd numbers? Do you know what is odd numbers? Can you give some examples for odd numbers? Some examples, please, for odd numbers. I can't hear. Okay, then for even numbers. So then how about this? Can you write 100 as sum of 5 odd numbers? Okay. So I will leave you to think. Please discuss that with your friends. So we will come back to our main session.
Yeah, so let me go to the second half of my talk. So I'm hoping to discuss a few things related to mathematics and computers. Right? So I know that you all are willing to do a course on software engineering, something in the field of computer science. And let me briefly tell you the relation between mathematics and computer science with an emphasis on software engineering at some point. Okay, so why mathematics is important to you and why mathematics is unavoidable if you are students in computer science particularly. So this is actually the second part, the human factor. That's the main title. So definitely a computer is a human invention, right? So it's humans who build the computers. So obviously this is related to that. So what is the mathematics that you need to operate a computer? Okay, so this is actually a separate branch in mathematics called computational mathematics. So this is my field of expertise in a way. So we are dealing with computers in different ways. One is actually we are making use of computers for mathematics. As mathematicians, we make use of computers. And on the other hand, we want to understand what a computer is. That is the other aspect. As software engineers, definitely you have to deal with mathematics, and this is something unavoidable. But on the other hand, this is something you can do definitely. I'll show you the reasons. And I'm not just claiming it without evidence, with some evidence and with some justifications. So I'll tell you why you can do mathematics very well, the mathematics needed for a software engineer particularly. And so this is the subject called computational mathematics, and it is twofold. One is we use computers to do mathematics, to do some mathematical operations. It is hard or impossible nearly to do manually. Then actually we seek the help of computers to do such tasks. That is one aspect. On the other hand, as I told you earlier also, we want to understand what computers are. Although humans have built these machines, humans did not understand what they are, and their capacity was not explored in those days. And still people are exploring what computers can do. And you know, now with the with the coming of this AI thing, right? And so there's a question whether we really know what computers can do. So they can do the tasks that are hardly imaginable to humans now, right? With the AI. And I think now this has become a problem in the society as well. So the AI is doing wonderful tasks, and sometimes it deceives us a lot, right? So what is the capacity of AI? Am I sharing? I think I'm sharing the screen. How about the centers? Is it visible there? Okay, it's working, right? Okay. Yeah. So also we want to understand what a computer is. So I was talking about this AI thing. And so still we don't know the limitations of computers. So this is a problem. So we need to know the capacity of computers and also the limitations of computers, right? What they can and cannot do. So this belongs to the other aspect. So this is twofold. Computers for mathematics, right? So we may have some problems, some real problems, and they require mathematical solutions, but impossible to compute manually. So we seek the help of computers. We use computers to solve those problems. That is one aspect. One aspect of computational mathematics, computers for mathematics. Okay, and then we have computer algorithms solve these problems. On the other hand, we want to understand what computers are. We want to model the computers themselves, okay, and to find out their real capacity and to know whether a task can be performed by a computer. What can it do? So this is the other aspect. So these are the two aspects of computational mathematics. So for the first aspect of computational mathematics, that is computers for mathematics. Now, okay, you are software engineers. Okay, one day you will become software engineers, and there is a problem. This simple problem, simultaneous equations. You all know what this problem is, right? Two variables, two equations, two variables. You can solve it manually. Okay, you see a system, simultaneous linear equations. 2x1 plus 5x2 is equal to 7. 3x1 plus 8x2 is equal to 3. If you take a piece of paper, you can solve it readily. The problem is there are so many real problems that transform into this sort of systems, but with hundreds or thousands of variables. That is a problem. Okay, so once you start practicing software engineering, you go to a company, you go to a client, you take a problem. That problem is about something else. Maybe it's about production planning and actually weather forecasting, right? Weather forecasting is a linear system. If you want to forecast the weather, there is a huge linear system, simultaneous equations, but there will be thousands of equations. So can you do it manually? No. So you have to write a program to solve it. Before writing the program, you need to know the mathematics of it. So you have to translate it into the mathematical language first, and then you translate it into the computer language. So this is the way, right? It's a way to go. So you have a real problem, then you translate it into the mathematical form. You realize, okay, it is a linear system, but with hundreds or thousands of equations. So definitely you can't handle it manually, and that's why you got computers. So you write a computer algorithm and you solve it. And this is one instance. If it is two variables and two equations, definitely you can handle it manually. You have handled that in grade 8 or 9, the simultaneous equations. But there are very nice algorithms, compute algorithms built on mathematical ideas that will solve these equations. So there is one application, one instance where computers help a lot to solve real problems. So mathematical way of arriving at a solution, there are mathematical algorithms. So we have such a thing as pseudocode, right? You don't write the thing, you don't start by programming it in a programming language, but you write the codes, you write it, you give the instructions, right? Algorithm is actually a set of instructions. a set of instructions that you give to a computer. Okay, so first you translate it to the algorithmic language, and then you translate it into the computer language. So this is how real problems are solved. Eventually, you give the commands that can be read by a computer, and then the computer will do the labor work for you. That's how it happens, right? So you have to make use of computers. Well, you are masters of computers, right? Not slaves of computers. Okay, so so you have to make use of them. All right, let them do the labor work for you. So in this aspect of mathematics, so there are real problems, and many real world problems have mathematical models. Otherwise, you can't solve them. So clients are giving you problems. They don't give you X's and Y's. No, they will give you problems. Okay, we have this sort of production, and we have these constraints. Well, we have this much of human hours, and we have this number of machines. Likewise, a client will give you a problem, right? Then you realize, okay, once you write it down clearly and logically, it turns out to be a mathematical problem, perhaps a set of linear equations, simultaneous equations. Okay, and then actually you have to solve them, and you have the mathematical formulation, impossible to solve manually. It has thousands of variables. So you give it to a computer. First, you write a pseudocode, and then you translate it to the machine language, something that can be readable to a computer, and eventually you solve it. And finally, you apply that solution to the real problem, and you are presenting it to the client. Okay, so this is one aspect of software engineering that you have to, as software engineers, perhaps you may have to do this sort of tasks, right? And there are some mathematical software packages, particularly designed to do mathematics. One is called MATLAB. So MATLAB is very good for things like, there are some particular things like calculus. There's a particular branch in mathematics called calculus. To do calculus, MATLAB is ideal. And there are some branches in mathematics like discrete mathematics or graph theory, some technical terms, right? I'm just telling you these things because some of these software are better for some purposes. So MATLAB is used extensively by engineers. So it's very good for engineering purposes. And Mathematica mostly used by theoretical physics people, and mathematicians use Mathematica. I think, and there's another software called Lingo. It is particularly for a branch called operations research, a particular branch in mathematics. So these are some mathematical software packages that you have to use, right? If you want to perform certain tasks, then you have to use some software packages. And the thing is, nowadays, Excel is something very common. You all know about Excel, right? Have you heard about MATLAB? Anybody who has about MATLAB before? But Excel, who has heard about Excel? Very good now, right? Okay. Excel is very common. Now, Excel, although Excel is not particularly designed to do mathematical tasks, nowadays, Excel is very rich, right? It's enriched with lots of mathematical features. So you can run many mathematical algorithms using Excel, including some complex algorithms, actually. These days, Excel is very advanced. So you can do lots of math on Excel. And everybody has heard about Python, right? Yes, on Python platforms, particularly using Octave. Actually, using Octave, you can write many MATLAB commands. So Python is a language that is very helpful for scientific computing purposes, particularly. So these are some platforms on which you can solve such problems, the things that you cannot do manually. Okay, you have to make use of the computers, let them do the labor work. So these are some platforms you might use, perhaps, right? And some tasks, some particular tasks, some probable tasks that you might get from a client, making a timetable. Making a timetable is a hard thing, right? Because actually, if there are any clashes in your timetable at the Open University, don't complain, because it is difficult to make a timetable, right? Do you think that making a timetable is an easy task? That you can make a timetable just if you know some coding? Very difficult, right? It's very difficult. So making a timetable is essentially a mathematical task, right? You have to take a particular time slot. And if this time slot is used by this particular person for this particular lecture, it is 1. Otherwise, it is 0. This is the standard way of formulating it, using what is called Boolean variables. You may have done some IT, so you may know the things like Boolean variables. And it is actually a math, right? It is math. So because there are some restrictions, You formulate the restrictions using mathematics. So timetabling is a mathematical task. To make a timetable, you need lots of math. Okay, to do it properly, to make a better timetable, to make a timetable without clashes, you need math. And it is a very elegant mathematical formulation called the timetabling problem. Actually, there are many scheduling problems in mathematics belonging to the branch operations research. Okay, so make a timetable, you may get this problem from a client. So how to handle it? You formulate it mathematically, and then you can use this platform Lingo. Right? Lingo is particularly for this sort of tasks, or even Excel works there, right? And then you can do the timetable and predicting, so forecasting. Okay, so you have some data. So how to forecast, how to predict about future. So this is one possible task that you may receive from a client in future. So how to handle this? Well, you have to give the problem to a computer. Okay, and actually production planning. So what do you have to make using this machine at this particular time slot? A very possible problem that might come from a factory. Okay, production planning. So this is a mathematical task that you need mathematics to solve that problem. Not just coding, right? Before coding, you need to know the math. You need to know how to translate it into mathematics and resource allocation. Now there are resources, and you need to find the best way to allocate these resources to small, to people or maybe to hospitals. During the time of COVID, how to allocate resources to the hospitals. So likewise, that sort of operations, right? The operations, they involve some decision-making process. And there's such a thing called decision support systems. So these are computer platforms that help people to make the best decision. So the computer will make the decision for the client, but you have to make the decision support system, right? Okay, to make the decision support system, you have to incorporate a mathematical algorithm into it to make the decision. The decision has to be made logically by using the deductive method, deductive logic, right? So it has to be reached logically. So to make decision support systems, well, in the process, lots of math is involved. So these are some tasks that I could think of. I just typed a few things that came to my mind. Some tasks that require a lot of math. As software engineers, right? Perhaps one day you may have to go through these things. Well, now go to the same example. Now I want to tell you a few things about the other aspect of computational mathematics. One aspect is you let the computers do the labor work. You make use of them, right? Okay, so if there are labor, well, if there are people to do the work for you, how to get the work done is one thing, right? And what is the other aspect? If you hire a person, suppose actually these days I'm hiring persons as caregivers to my father who is very old. So I have hired many people as caregivers. So what are the things that I have to be careful? What are the things I have to look into? If you hire a person, to do some work, maybe some work in your garden, the first thing is how to get the work done by that guy. Agreed? Well, if that person, whether the person can, first you should know how to get the work done by the person, right? Person you are hiring, that is the first thing. So this is what we have discussed. There are platforms, how to get the work done using computers. There are some computational platforms, right? First the mathematical formulation, and then the computer algorithm, and then the machine code. One thing. The other aspect is, can the person do it? And what else can the person do? Will the person harm your sick father? Will the person ruin your garden? Can the person do that task? So understanding the person is the other aspect. If you're hiring someone, first you should seek for the ways, first you should check whether you can, how to get the work done by the guy. One aspect. The other aspect is you should know something about that person. Can he be a terrorist? Can he be a thief? Right? So you should know something about computers on the other hand. You should know something about the computer's capacity. You should know what a computer can do and what it cannot do. This is the other aspect of computational mathematics. Understanding what a computer is. Got it? First, you make use of computers. First, the first component of computational mathematics is about it. Making use of computers. The other aspect, what is a computer? So philosophical understanding of a computer, right? So it's a philosophical question. What a computer is, what the hell the man has built. And what is going to govern the world in future, right? So what is this funny device called the computer that everybody has, at least in the form of a smartphone? Okay, so we need to know about it, and it is not just a philosophical question. This is something very pragmatic. For example, if you want a computer to solve a system of equations, simultaneous equations, you see, right? Now you give the computer the task. You should know whether the computer can do that task or not. This is called computability, right? So certain things are computable and certain things are not computable. Some tasks can be performed on a computer and some tasks cannot, right? So we should be aware of that aspect as well. And this makes a special branch of mathematics called theoretical computer science. Also, if you can do the task, right? Now, suppose you hire a man to do your work in your garden, right? And then actually you should know how much time this man consumes and how much food he needs, maybe. Okay, and how he's going to do the task. So these are the other questions. So if you use a computer to solve this sort of system, then you should know first whether it's solvable or not using a computer, computable or not. If computable, how much time does the computer take to do the task, and how much memory it requires to do the task? You have the RAM of computer, right? So how much memory or how much space does the computer require? Well, if you have a system of, let's say, 10,000 equations and 10,000 variables, 10,000 equations, 10,000 variables, but your computer's RAM is sufficient only to handle this problem with maybe 5,000 variables and 5,000 unknowns, right? And it is beyond the capacity of your computer. So this is actually called the complexity analysis. Okay, the computational complexity, whether you can, whether you can do this efficiently or not within a reasonable time period using a reasonable computer memory or not. This is very important. So this is the other aspect of computer science, that is mathematics of computers. You are analyzing a computer by developing a model for a computer, and then you are analyzing it mathematically, logically, by the deductive method, obviously, right? And you are coming to conclusions. You are coming to know the computer. You are coming to know this strange person called the computer, what that person can do and what that person cannot do, the limitations and the capacities. So you are going to know about these things, right? So this is actually the subject pioneered by the well-known mathematician Alan Turing. Heard about Alan Turing? Enigma code, Enigma machine. There was a famous movie as well. Okay, you know about Alan Turing. Okay, so Alan Turing was the pioneer of this sort of science, the science of knowing what a computer is. This branch of mathematics called theoretical computer science. Okay, so he built a hypothetical device, or he gave a model for a computer that consists of an infinite table, right, resembling the memory of a computer. And there's a pointer, that there's a head. We call it the head. In our language, we call it the head, which can move. You can move the head, and then you can read the entry, and it has a one-time memory. You can keep it in the memory, and then the head can move. Likewise, whatever you can do on a computer or the smartphones you have can be simulated on this machine. If you have a very long tape, okay, made of cells like this, whatever you do on your computer, even that activity you have done on your smartphones, well, that can be simulated on that sort of device, and then it becomes mathematics. Analyzing what it can do and how many moves you have to make, how many times you have to move the pointer to different cells, right? How many cells you have to pass, and how much space you require. So it is actually the computational complexity theory, and the ability to do the task also can be checked from Turing's model, from the model Alan Turing built. So this is actually what we study under theoretical computer science. A few things about Turing machines, how it works. It's a hypothetical device, right? And therefore it is mathematics. And so this belongs to a separate branch of mathematics called discrete mathematics. Now earlier I talked about mathematical logic, the rules of the game. I told you that if you know the rules of the games, then you can play the game. Okay, that is logic, mathematical logic. And also the theoretical computer science. They also, so these things, they also belong to the branch of discrete mathematics. What do we mean by discrete? Discrete and continuous, two opposites. Discrete and continuous. Zeno, Parmenides, right? Socrates said, you can break things into small parts. And Parmenides said, no, it is a continuum. You can't break the universe into small parts. If you can if you can discretize things, if you can break down large things into small parts, and if there are something such as the consecutive element, the next element, that becomes discrete. Okay? And if you cannot break it into parts, that is called continuous. Vaguely speaking, right? Loosely speaking, that is what we mean by continuity, and it is the opposite is discrete. Okay, here's a very well example that makes sense. Continuous. If you want beats, if you want in kilograms, let me say, if you want 1.53 beats, can you get it? First diagram, yes, you can. In any quantity, you can get the beats. If you want, well, not from a shop, but if you go to the supermarket, you can get in any quantities, right? Supermarket 1.53 kilograms beats then again. But if you go to the supermarket, Cargills or Kills, of course you can get. They have their weighing machine, so you just put and you weigh about 1.53 kilograms and you can get it, right? So available in arbitrary quantities, that is continuous. But you cannot get 1.53 cans of beans. Definitely it has to be a whole number, right? Okay, if you want 1.53, how many cans you have to get? If each can weighs 1 kilogram? Not a very serious question too, right? You need 2 cans, okay? Yes, I just wanted to check whether you are awake or not. Okay, I think you are paying attention, thank you. The thing is, that is called discrete, okay? Discrete, the difference between discrete and continuous. Now, Zeno argued, Parmenidean school, so they thought the universe is a continuum, it is continuous. It cannot be broken into tiny parts. But on the other hand, some other philosophers argued that it can be broken down into tiny parts. The difference between continuous and discrete, whether the universe is continuous or discrete, that debate was there 3,000 years ago even, right? It's a very long debate whether the universe is continuous or discrete, but I'm not talking about philosophy now. I'm just telling you the difference between continuous and discrete. Now, the mathematics needed for computer science is mostly the discrete mathematics. A few more examples. So this is a continuous data set, continuous, continuity. And this is discrete, scattered, you have such a thing as an X point, right? One by one, you can count them. Discrete data set, continuous data set. The continuous one, you can plot it without lifting your pen. There you have to lift your pen to plot those to plot those things. Anyway, the difference between discrete and continuous. It is discrete mathematics that is essential to learn computer science. Okay, for computer science students, particularly for software engineering, discrete mathematics is essential. Some branches, some subjects in discrete mathematics, logic, that's where the rules of mathematics are set. You have to be experts on those rules. And set theory, Venn diagrams, those things, right? Venn diagrams, okay, algorithmics. Okay, now there are algorithms, sets of instructions to do certain tasks. And analysis of the algorithms is called algorithmics. So the study of algorithms, that belongs to discrete mathematics. And combinatorics, it's about counting things. Okay, for example, if I say, well, there are 3 ways to enter this room, 3 doors to enter the room, and 4 doors to leave the room. How many ways are there to enter and leave the room? Likewise, you can count things like that. Okay, it's about counting, mostly about counting and about permuting things, rearranging things, combinatorics, and then computability. We already had the talk. Whether this task can be performed on a computer or not, that is called computability. Okay, and complexity. How much time does it take? How much time does a computer take to do this task? And how much space or how much memory the computer requires to do the task? That belongs to the field of complexity, right? So these are some branches in discrete mathematics that will be very important to you. The thing is now, because I think most of you, or all of you maybe in the audience and students, So you are coming from non-mathematics backgrounds. Once again, I have to say that never feel that you are inferior, right? Because even in Sri Lanka, in our advanced level mathematics curriculum, if you review the combined mathematics curriculum, most of the mathematics covered there, most of the topics, they are about continuous things. Okay, only a very few sections. There are some sections called a few names, permutations and combinations. Well, I was thinking, is that all? Yeah, binomial theorem, matrix algebra. That's all I could find out because I was making the slides. I was just thinking of the advanced level curriculum. So very few things, only a very few elements, right? So don't think that they are superior and you are inferior. No, it is not the case. And I'm obviously I'm working with them, right? And I know where they are. So never feel that you are inferior and they are superior and they will outperform you. No, don't think like that. There's no competition. First of all, there's no competition because it is about knowing something, understanding something thoroughly, and then actually it is about doing a task properly, right? Mathematics is about that. Deductive logic, reasoning properly, right? The no competition. But on the other hand, if you feel in any way, if you feel that you cannot do it, no, definitely you can do it for this reason. Because it is a fresh start. And most of the discrete mathematics topics are new to both, to all the, I think to all university students, it is really new, right? So your and your view on mathematics, I don't blame you. If you view mathematics as a difficult subject, I did the same. When I was doing, well, I was in grade 10, I did the same. I viewed it as a difficult and a very, something that is not really, I thought it is not my cup of tea, right? But the things change a lot. So it's about the attitude and it's about the view, and you are going to get the proper taste of mathematics at the university, at your first year, with the logic and all those things, right? With your curriculum, the logic, especially with mathematical logic, you are going to get the taste of real mathematics. And there may be many students here in this audience who might do very well in mathematics. Just take my word. Because we are running an external degree, right? We are not just taking people from mathematics stream. No. At University of Colombo, at the Department of Mathematics, we are running an external degree on financial engineering. Actually, Dr. Lakshmi is also a contributor to that. So she's teaching courses there. So she also may confirm it. We are receiving students from other disciplines. And they are, some of them are actually outperforming the others, right? So it is not whether you have done mathematics at advanced level or not. No, it doesn't matter. So this is a fresh start, and this is a new branch of mathematics. And why don't you look at it with fresh eyes and have a good start, and don't panic when you see formula. But once you know the rules, I repeat, once you know the rules, the game will be very easy. Okay. So the rules are there taught at when you do the course on mathematical logic, the rules will be taught. So it is a fresh start, and for reasonable, on reasonable grounds, I'm pretty sure that if you work properly, not just hard work is actually not the time you spend to do it, right? So never compromise on fundamentals, particularly on logic. Never compromise. Just work hard until you understand the foundations. Then the rest will be very easy. Okay, and there will be an activity. I don't know whether we have enough time for an activity or not. You can do the activity once you go home even. So normally, I told you that most of the mathematics in advanced level designed to cater to the continuous branch of mathematics. And actually, it is the engineers who make use of the continuous mathematics very often, right? Mostly, it's about engineering. And for computer science, it is mostly the discrete part. So the engineers are working with such a thing called differential equations, right? And even as mathematicians, we deal with differential equations. But for you, I'm just showing the difference, right? So it is the difference equations, the kind of discrete counterpart of differential equations. It is difference equations. So we designed an activity called the Tower of Hanoi. An activity will be there in your system. So just go home and leisurely you can do the activity that is on difference equations. I just wanted to show you the difference and the algorithmic thinking. You need to have a good algorithmic thinking. So this is a task you can do, a kind of fun activity as well. Just try it. it is related to difference equations and recurrence relations, right? And so just one other thing, because in Sri Lanka, so as a professor in computational mathematics, I regret to say that in Sri Lanka, we have a tendency of ignoring mathematics in computer curriculums. Okay, in India, it is not the case, because I have many colleagues in India and I have been following Indian academia for a while. What I have observed is, if you type those things I told you today, some of the words you heard, like Turing machines, okay, and see where these tutorials, see where those lecture notes are coming from. Just type Turing machines in YouTube, right? Just do it. Even if you type Turing machines in YouTube, right? Just go home and type Turing machines, and there will be a bunch of videos coming from Indian institutions, right? Indians did not drop the mathematics needed to do the computer science, and there are lots of textbooks in India on computational mathematics, stressing on the important parts of mathematics to do the computer science. In Indian curriculums of computer science, you see lots of mathematics. Unfortunately, in Sri Lanka, we, at one point, I have to say, I regret that at one point we chose not to do that sort of mathematics, and in a way, silently and slowly, we have dropped the mathematics part. Okay, assuming it is not essential for software engineering and other disciplines in computer science. Now, actually, we are paying for that. You see where the Indians are. Now they are launching rockets to the moon, and you know where we are, right? So they did not question the inclusion of mathematics. Normally, the Indians don't question Pandithatnaya again, right? But we question, are we going to use these things? What is the application? What is the application? And we keep questioning, but we question without searching what it is. So you have to search, you have to do some self-work, and you have to find the application at some point, right? So you have to know the rules first. If you know the rules, you can do wonderful things. Just take my word, because I was also not good at mathematics first. But once I started enjoying, and particularly when I got to see the rules of logic, then actually that was a fresh start, and I don't see any reason why that the same thing won't work for you, right? So the Indians are, miles ahead of us in computer science. In Silicon Valley, you see many Indians and doing wonderful things. Unfortunately, we did not take the mathematics seriously at one point in our history, and that is a major mistake we did. Now, so I'm really glad that in this curriculum of the Open University, now you have a very good mathematics component, and they have this bridging or the gap filling course as well. So just take it seriously, and especially the mathematical logic, the rules, and then you can follow the rest of the things very well, I hope. So I wish you all the best, and let me conclude my talk, right? Okay, thank you so much.
Thank you, Professor Radhakrishnan. So we hope that today's workshop contributed to enhance your liking to the subject of mathematics. So what do you think? Okay, so I really appreciate Professor Radha Mahasinghe to accepting our invitation, being with us today, presenting a very interesting and thoughtful talking presentation on the beauty of mathematics, contribution of mathematics for computing. Professor Mahasinghe, thank you so much for being with us as the resource person and giving valuable insights of our students. Thank you so much. Yes. And so we will wind up the session from here. Thank you everyone for all the supports and participation, and for our centers. Thank you so much for your support. And for all the students, I wish you all the best, and we will stay in touch during this course, and hope to see you in future. Okay, thank you.